Justin Hutches, and I'm going to talk about the vapor compression refrigeration / heat pump. A little introduction. The experiment is used to analyze the performance of a heat pump. The heat is absorbed from low temperature source and it is released into a high temperature source. And the objective of this experiment is to learn how to perform thermodynamic analysis of a heat pump and measure coefficient of performance and describe the vapor compression refrigeration cycle and pH diagram. The coefficient of performance is a ratio of the magnitude of desired commodity to the magnitude of expenditure. The expenditure is power consumed at the compressor, and the desired quantity is either the refrigeration or the heating. Enthalpies are deduced by placing temperature and pressure transducers at various locations around the refrigerant loop, and all of this is used to calculate the COP. Looking at the pH diagram for vapor compression, this includes compression of the refrigerant, which is from 1 to 2. This is high pressure and high temperature. And then condensation, which is from 2 to 3. This is heat rejection. And then expansion and evaporation, which is 3 to 4 and 4 to 1. This is low pressure and low temperature, and all this transfers heat and provides cooling. The thermostatic expansion valve, this controls the rate of flow of liquid refrigerant into the evaporator. It's controlled by the sensing bulb, which is that purple flow up top that goes down towards the bottom of the figure. The refrigerant enters the valve under high pressure from the liquid line, and pressure is reduced when the valve limits the amount of liquid. The red line is coming from the condenser, the blue line is going through the evaporator, you have your fan that's cooling it down, and you have your gauge in the bottom left-hand corner. Some experimental data. This was taken from the heat pump. In the beginning, we set the water inlet flow at 5.1. That was as close as we could get it to 5. The temperature of the water at the outlet of the condenser was 25.9 degrees Celsius. Temperature of the water at the inlet of the condenser was 22 degrees Celsius. And the power consumed by the compressor was 0.399 kilowatts. This was data taken at various water inlet flow levels. We had 6 liters per minute, 4.5 liters per minute, and 3 liters per minute. We had the cooling pressure at the inlet of the compressor, which was sensor SP2 and their respective values. The cooling pressure at the outlet of the condenser, which was sensor SP1 and their respective values. Cooling temperature at the inlet of the compressor, which was sensor ST2. Cooling temperature at the outlet of the compressor, which was ST1. Cooling temperature at the outlet of the condenser, which was ST3. And cooling temperature at the outlet of the expansion valve, which is ST4. This here I calculated the COP. COP is Q over W, which Q is the mass flow rate times the specific heat times the change in temperature. And that W value is this power consumed value from beforehand. So I went through and used the different mass flow rates for the 6 liters per minute, 4.5 liters per minute, 3 liters per minute. I used that mass flow rate times specific heat of water and the change in temperatures, which was on the last table, and divided by the different power consumed to get a COP for 6 liters per minute of 3.16, for 4.5 liters per minute of 3.09, and 3.08 for 3 liters per minute. This was compared to 2.5 predicted by the group leader. Some sources of uncertainty were not allowing the system to reach equilibrium each time, not setting the water flow to the correct value because the system was very hard and very sensitive, not setting the water flow to the correct, I'll skip that. Inputting data incorrectly, the heat of the room that the system's in possibly, and or touching the system could all be factors that could change our values. And these are my references. Any questions?